Hi everyone. In this session, let's take a look at threads and also the concept of multi-core programming. So specifically, let's look at what a thread actually is and why we would use threads, and then the benefits of threads. Then we'll take a look at the idea of and the concept of multi-core programming, and then some of the challenges that are involved with creating applications that take advantage of multi-core programming. And then lastly, we'll look at some types of parallelism. So threads. So modern operating systems allow for multiple threads of control. And a thread is what we would call a basic unit of CPU utilization. And it consists of a thread ID, a program counter, a register set, and a stack. So each thread has its own set of resources. And it shares code, it shares data and resources with other threads that belong to the same process. So a process might be a particular application. And so an application, when we create that application, we can code it to spawn threads that each has its own tasks that it needs to perform. So a traditional process has a single thread of control. So it's what we call single-threaded. So it's what we see here in the left diagram. So a single-threaded process, where this thread has code, data, files, and then it has access to registers in a stack. So this is one thread with these resources. Now, if a process is multi-threaded, it can perform more than one task at a time. So we can see here over in the right diagram, we have what we would call a multi-threaded process. So this multi-threaded process, you can see that it shares code, data, and files, but it has its own access to registers and it has its own stack. Okay, so this is multi-threaded as opposed to single-threaded. Now, most applications in modern systems are what we would call multi-threaded, and I have an example here that I'm going to discuss in a minute. So a modern web server, as an example, handles thousands of requests simultaneously, so at the same time. And it does this with multi-threading. So for example, Internet Information Server, if we're running that on a Windows server system, or Apache server if we're running it on a Linux system. These two applications are multi-threaded examples of multi-threaded applications that handle web serving. So with these applications, each request the process creates another thread to handle it. So the web server creates a thread for each request. So if we look here over on the left-hand side, here we have a client. Okay, so a client's accessing a browser and they're making a request to the web server here. And what the server does then is it creates a new thread to service the request. So for example, the client may be wanting some information about some products. So the server creates a thread that then goes off and handles that request. So maybe it makes a request to a database that then retrieves some information and sends it back. So that thread is servicing the request of this client. But as we know, if we have a website that's quite large, we may have potentially thousands of clients accessing that website at the same time. So what happens then is the server creates the thread and then it goes back to listening for more requests. And it does this super quick, right? So of course, we want to have a web server that can handle these multiple requests that are coming in smoothly, efficiently, without any lag time. Okay, so again, we may have thousands of client requests at any given time where the web server processes those requests by creating new threads. Okay, so any web server should have the ability to quickly and efficiently create threads and go back to servicing more requests. So what are some of the benefits of multi-threading? Well, we've just seen an example there with a web server. Other benefits include the idea of responsiveness. So it allows programs to continue running even if part is blocked or part is busy. So it needs to be responsive. So a single-threaded app would not be able to continue, for example, because it's servicing a particular request. Another benefit is the idea of resource sharing. So threads share memory and resources of the process that they belong to. So multiple threads, as we've seen, share the same resources. And the advantage of that, in one sense, is that those resources are independent of any other resources that are running for other applications or that have been allocated for other applications. So it allows the app to have multiple threads of activity in the same address space. So in that sense, the resource sharing is a little bit more efficient. Which takes us to the idea of economy, where allocating memory and resources for process creation is costly. So if multiple threads share those same resources, that's efficient. So threads share resources of their shared process. So it's a good model for economy. And then the other concept is the idea of scalability. So in a multiprocessor system, threads may be running in parallel on different processing cores. And we'll take a look at what that looks like in just a minute here. So single-threaded can run only on one processor, right? But if we have multi-threading, we can actually share the load across those multiple processors. So with multi-core programming, single CPU systems have evolved nowadays into multi-CPU systems, so very common. And then the next step to having multiple computing cores actually on one chip. So each of those cores executes independently of the other cores. And so these are called multi-core or also multiprocessor systems. And multi-threaded programming then, if we write code that takes advantage of this, it allows for efficient use of these multi-core systems so we can better take advantage of them with some good coding techniques. And so the coding then, if we do it correctly, allows for threads to run truly in parallel, which is better than the idea of concurrency, which is where threads share access to the CPU one at a time. But with concurrency, of course, it happens so quickly. When we go between threads that are executed one by one on the single core that we may have, for example, it appears to be happening in parallel, but in fact, it's happening in concurrently. So I'll show you a diagram of this in a sec. Let's take a look at it right now. So there is a difference then between parallelism and concurrency. Okay, so it is possible to have concurrency without parallelism. So parallel execution truly means more than one threading running at the same time. So with this diagram here, essentially we have 4 threads. Okay, on core 1, we're running threads T1 and threads T3. Okay, and then on core 2, we're executing threads T2 and threads T4. Okay, so if we look at core 1 to start with here then, what we're doing is concurrency with threads T1 and T3. So you can see then that these threads are sharing execution time on the CPU by executing T1 first and then T3. So each of these is getting a slice of time essentially on the processor if we're using time slices. And this is happening concurrently. So T1, T3, T1, T3. That's concurrency. And same thing on core 2. T2 and T4 are running concurrently on core 2, right? Where T2 gets a slice, T4 gets a slice, T2 gets a slice, etc. So concurrency again here. But these threads, T1 and T2, let me change the color here. These threads are running in parallel, right? So if we look at it, T1 and T2 are running at the same time, one on core 1, one on core 2. That is parallelism. So we can have concurrency and parallelism occurring at the same time if we have a multi-core system. Okay, so concurrency on core 1, T1 and T3, parallelism on core 1 and core 2 with T1 and T2. Okay, so hopefully that makes sense how we differentiate between the idea of concurrency and parallelism. So CPU designers improve system performance then by adding hardware to improve thread performance, right? So multiple threads can be loaded into the core for fast switching. Some of the programming challenges around this though. So with multi-core systems, better scheduling algorithms must be designed to allow for this truly parallel execution, which we saw in the previous diagram there where T1 and T2, thread 1 and thread 2 were operating in parallel. But this takes some special coding in order to ensure that this happens efficiently and effectively. So for programmers, the challenge is to modify existing programs and design new multi-threaded programs that take advantage of multi-core systems. So what are the 5 main areas, the 5 main challenges? Well, first of all, identifying tasks. So we need to be able to find areas that can be divided into concurrent tasks. So for example, coding where T1 and T2, thread 1 and thread 2, one uses core 1, thread 1, and thread 2 uses core 2. Also, we need to find balance. So when identifying parallel tasks, the designer must ensure that the tasks perform equal work, right? So that the load is shared across both of those cores, if we're referring to the previous example. And then each thread may be accessing data, right? So data splitting becomes an issue. So data must be divided to run on separate cores. So we have to think about that and manage that effectively. Then data dependency. So one task may depend on data from another. So how do we handle that, right? That can be an issue. If one thread is waiting, for example, for another thread to complete before it accesses that data, then we have to take that into consideration when we're writing our code. And then lastly, testing and debugging. So more complex code when we're handling multi-core systems means that there's more complexity involved in testing and debugging those programs. Okay, so these are some of the programming challenges when we're dealing with multi-core systems. Some different types of parallelism. Well, data parallelism focuses on distributing subsets of the same data across multiple cores. So then we perform the same operation essentially on each core. Next, we have task parallelism. So the distribution of tasks or the distribution of threads across multiple cores. So that takes a little bit of consideration. So each thread performs a unique operation. So in that sense, we can send one thread to one core to do its operation and then another thread to another core to do its operation if they're unique. But that may be on the same data or it may be on different data. So we have to take that into consideration as well. So data parallelism and task parallelism. In most instances, applications use a hybrid of the two. So again, we have to be careful in our consideration of how we write the code to take into account both data parallelism and task parallelism. All right, so just to summarize what we talked about today in this session, we looked at what is a thread and why we would use threads. So with an application, we can create multiple threads, which can be run on our CPU that allow us to use our processor more efficiently, for example. We looked at the benefits of threads. Again, with multi-threading, we can optimize access to our processor or processors if we're dealing with more than one. We looked at the idea of multi-core programming, so the ideas of concurrency and the ideas of parallelism and how they fit together. We looked at some of the challenges of multi-core programming. So from a coding perspective, there are some issues around multi-core programming, for example, shared data access. And then lastly, we looked at different types of parallelism, so data parallelism versus task parallelism. So thanks for tuning into this session, and we'll see you folks in the next session.